Yeah, day 40. So let's continue with 5.6, the normal distribution. The bell-shaped normal distribution appears naturally in many applications. For example, the heights and weights of newborns, the lifespans of many consumer items such as light bulbs, and many standardized test scores are well described by the normal distribution. Variables are that the end result of multiple random influences tend to exhibit a normal distribution. For example, the error of a machine that aims to fill containers with exactly 1 gallon of liquid might be expected. Uh, By the same logic, because rates of returns are affected, because rates of return are affected by multiplicity of unanticipated factors, they also might be expected to be at least approximately normally distributed. To see why a normal curve is normal, consider a newspaper stand that turns a profit of $100 on a good day and breaks even on a bad day, with equal probabilities of 0.5. Thus, the mean daily profit is $50. We can build a tree that compiles all the possible outcomes at the end of any period. Here is an event tree showing outcomes after 2 days. 2 good days profit 200, 1 good day, 1 bad day profit 100, 2 bad days profit 0. Notice that 2 days can produce 3 different outcomes, and in general n days can produce n plus 1 possible outcomes. The most likely 2-day outcome is 1 good day, 1 bad day, which can happen in 2 ways. First, a good day, or first a bad day. Probability of this outcome is 0.5. Less likely are 2 extreme outcomes. Both good days or both bad days, with probability 0.25 each. What is the distribution of profits at the end of 200 days? There are 201 possible outcomes, and again, the mid-range outcomes are the most likely because there are more sequences that lead to them, while only one sequence can lead to 200 consecutive bad days. An enormous number of good and bad days result in 100 good days and 100 bad days. Therefore, mid-range outcomes are more likely. Mid-range outcomes are far more likely than are either extremely good or extremely bad outcomes, just as described by the familiar bell-shaped curve. Figure 5.3 shows a graph of normal curve with mean 10%, standard deviation 20%. Smaller SD means that the possible outcomes cluster more tightly around the mean, while a higher SD implies more diffuse distributions. The likelihood of realizing any particular outcome when sampling from a normal distribution is fully determined by the number of standard deviations that separate the outcome from the mean. Put differently, the normal distribution is completely characterized by 2 parameters, the mean and the standard deviation. Investment management is far more traceable when rates of returns can be well approximated by normal distribution. First, the normal distribution is symmetric. That is, the probability of any positive deviation above the mean is equal to that of the negative deviation of the same magnitude. Absent symmetric, the standard deviation is an incomplete measure of risk. Second, let's just read that again. Investment management is far more traceable when rates of return can be well approximated by normal distribution. Investment management is far more traceable when rates of return. First, the normal distribution is symmetric, that is, the probability of any positive deviation above the mean equal to that negative deviation of the same magnitude. Absent symmetry, the standard deviation is an incomplete measure of risk. Second, the normal distribution belongs to a special family of distributions characterized as stable because of the following property. When assets with normally distributed returns are mixed to construct a portfolio, the portfolio return is also normally distributed. Third, scenario analysis is greatly simplified when only 2 parameters, mean and SD, need to be estimated to obtain the probabilities of future scenarios. Fourth, When constructing portfolios of securities, we must account for the statistical dependence of returns across securities. Generally, such dependence is a complex multi-layered relationship, but when securities are normally distributed, the statistical relation between returns can be summarized with a single correlation coefficient. How closely must actual return distributions fit the normal curve to justify its use in investment management? Clearly, the normal curve cannot be a perfect description of reality. For example, actual returns cannot be less than 100%, which the normal distribution would not rule out. But this does not mean that the normal curve cannot still be useful. A similar issue arises in many other contexts. For example, birth weight is typically evaluated in comparison to a normal curve of newborn weights. Although no baby is born with a negative weight, the normal distribution still is useful here because the SD of the weight is small relative to its mean, and the predicted likelihood of a negative weight would be too trivial to matter. In a similar spirit, we must identify criteria to determine the adequacy of the normality assumption for rates of return. The normal distribution with mean 10%, standard deviation 20%. As we can see from this diagram, the empirical law or whatever, that 68.26% of the data lies within one standard deviation, 95.44% lies within two standard deviations, and 99.74% of the data lies within three standard deviations, and the point 26% of the data lies beyond three standard deviations, known as outliers essentially. Example 5.10, normal distribution function in Excel. What? Support the monthly approximate normal distribution with the mean of 1%, standard deviation of 6%. Mean of 1%, standard deviation 6%. Provided the return index in any month below zero. So below zero would be only the return on the index only below minus 15%. Four, three, three, 8. I don't know this one. Check the this is the Excel stuff. We can leave this. Anyways, 5.7, deviations from normality and alternative risk measures. As we noted earlier, but you can't repeat it too often. Normality of excess returns hugely simplifies portfolio selection. Normality assures us that the standard deviation is a complete measure of risk, and hence the Sharpe ratio is a complete measure of portfolio performance. Unfortunately, deviations from normality of asset returns are potentially significant and dangerous to ignore. Deviation from normality. Yeah, okay. Statisticians often characterize probability distributions by what they call their moments, and deviations from normality may be discerned by calculating the higher moments of return distributions. The nth central moment of a distribution of excess returns R is estimated as the average value of R minus R bar to the power n. The first moment n equals to 1 is necessarily 0. Average deviation from the sample average must be 0. The second moment n equals to 2 is the estimate of the variance of returns, sigma squared. Measure of asymmetry called skew is the ratio of the average cube deviations from the sample average called third moment to the cubed standard deviation. Skew is the ratio of the average cube deviations third moment to the cube standard deviation. Yeah, okay. And the fourth moment is the kurtosis. We know that. So there it is, actually. This is pretty aligned with my courses right now, so that's pretty cool, right? When a distribution is skewed to the right, most of the extreme positive values are cubed. 5.48 dark curve positively skewed. Okay. Cube dominate the third moment in positive skew. When distribution skew to the left, the cube extreme negative value dominate. Skew will be negative. Okay. That is the negative one. Okay. When the distribution is positively skewed to the right, standard deviation overestimates risk because extreme positive surprises. Standard deviation overestimates risk. We should not concern investors. Nevertheless, increase the estimate of volatility. Conversely, and more important, when the distribution is negatively skewed, the standard deviation will underestimate risk. Another potentially important deviation from normality is kurtosis, concerns the likelihood of extreme values on either side of the mean at the expense of a smaller likelihood of moderate deviations. Graphically speaking, when the tails of a distribution are fat, there is more probability mass in the tails of the distribution than predicted by the normal distribution. That extra probability is taken at the expense of slender shoulders. That is, there is less probability mass near the center of the distribution. Figure 5.4b superimposes a fat tail distribution on a normal distribution with the same mean and SD. Although symmetry is still preserved, the SD will underestimate the likelihood of extreme events, large losses as well as large gains. Kurtosis measures the degree of fat tails. We use deviations from the average raised to the fourth power, the fourth moment of the distribution, scaled by the fourth power of the SD. Kurtosis equals to average minus 3. Okay. We subtract 3 in the equation because the expected value of the ratio for normal distribution is 3. Thus, this formula for kurtosis uses the normal distribution as a benchmark. Kurtosis for the normal distribution thus in effect defined as 0. So kurtosis above 0, sign of fatter tails. The kurtosis of the distribution in figure 5.4b, which has visible fat tails, is 0.35. 5.4b kurtosis. How is this fat tail though? I mean, I guess, I don't know. Normal fat tail. Distribution. Oh, because this is more than this. Okay, makes sense. This is finally making sense. Like, I've done stats and ecotricks for a while now, but this book is what makes it all connect, and I just need to keep doing it. And yeah, it's like every time, every time I get into the flow and I realize that this is it for me, and then I just can't be consistent, so I lose focus and I lose sight of the track essentially, and I start thinking, what am I doing with my life, and what am I supposed to do, what is my thing. But then eventually a few weeks or a month will pass and then I'll come back to the book, and then a couple of sessions in, or maybe one session or two sessions in, and I'll realize that yeah, this is it for me. Or maybe it isn't, but like this is what, out of everything that I've tried or done, even including music, like this is the most sort of cool thing. Even though I'm not a numbers guy, but it still feels cool to do this. Anyways, let's keep going and not waste time. We have 10 more minutes, so let's try to cover as much as we can. After this, I'll go do some cardio. Pretty much, yeah. Notice that both skew and kurtosis are pure numbers. They do not change when annualized from higher frequency observations. Higher frequency of extreme negative return may result from negative skew or kurtosis fat tail. Therefore, we would like a risk measure that indicates vulnerability to extreme negative returns. Concept check 5.7. Estimate the skew and kurtosis. The 5 holding period returns in spreadsheet 5.2. Spreadsheet 5.2 is not that. This right here. Sure. 5.2. Skew and kurtosis are the 5 holding period returns in spreadsheet 5.2. 5 holding period returns, okay. Year 1. Skew and kurtosis. Skew would be we just need the what do we need? Okay, squared deviation. One sec. I'm sort of confused, but one sec. Okay, so supposed to find out the skew, which will be the Q. Okay, the difference. What is the sum of the difference? You find out squared deviation. Squared deviation. That's squared though. I guess, okay. So for the year 1, I'm just gonna do I've tried this method out for year one, and I check the answer, and if it's correct, then I do for the other four. Okay, so square deviation is 0.0196. Square deviation is 0.0196. We just take the square root of this. We have 0.14. Okay, how about we cube 0.14? 0.0027 divided by 0.0027. Okay, 0.0027. 0.0027. 0.0027. 1 sec. 0.0055. 0.0027 by 0.0055. What was it? 25. 1 sec. 0.0027. 0.49. Is that normal? Okay, let's see if that makes sense. What? Use 5.19. Yeah, okay. To obtain skew and kurtosis historical sample Excel functions. Also, maybe this is not obtainable by maths, like we can't do it by hand. It's something to do with Excel, so have to put a hold on that right now. But yeah, okay. What was the slide? The higher frequency of extreme negative returns may result from negative skew and or kurtosis fat tails. Therefore, we would like a risk measure that indicates vulnerability to negative returns. We discuss 4 such measures that are most frequently used in practice: value at risk, expected shortfall, and low partial standard deviation, and the frequency of extreme 3 sigma returns. Value at risk. The value at risk denoted VAR. To distinguish it from VAR, the abbreviation for variance is the loss corresponding to a very low percentile of the entire return distribution. For example, the 5th or the 1st percentile return, VAR, is actually written into regulation of banks and closely watched by risk managers. It is another name for the quantile of a distribution. The quantile Q of a distribution is the value which lie Q% of the possible values. Thus, the median is Q equals to 50th quantile. Practitioners commonly estimate the 1% VAR, meaning that the 99% of returns will exceed the VAR and 1% of the returns will be worse. Therefore, the 1% VAR may be viewed as the cutoff separating the 1% worst case future scenarios from the rest of the distribution. When portfolio returns are normally distributed, the VAR is fully determined by the mean and SD of the distribution. Recalling that minus 2.33 is the first percentile of the standard normal distribution, with mean equals to 0 and SD equals to 1. The VAR for a normal distribution is VAR 1% normal equals to mean minus 2.33 SD. So let me read that again. When you're interested in noting VAR, distribution deviation for variance is a loss corresponding to very low percentile of the entire distribution. For example, the 5th or 1st percentile return, we are actually written to regulation of banks and closely watched by risk managers. It is another name for the quantile of a distribution. The quantile Q of a distribution is the value below which lie Q% of the possible values. Thus, the median is Q equal to 50th quantile. Practitioners commonly estimate okay. Practitioners commonly estimate the 1% VAR, meaning 99% cutoff, separating the 1% worst case future scenarios from the 1%, 1%. For returns are normally distributed, the VAR is fully determined by the mean and SD of the distribution. Recalling that minus 2.33 is the first percentile of standard normal distribution with mean equal to 0 and SD equal to 1. The the value at risk for normal distribution is mean minus 2.33 SD. To obtain a sample estimate of value at risk, we sort the observations from high to low. The variance, keep calling it the variance. The value at risk is the return at the first percentile of the sample distribution. Expected shortfall. When we assess tail risk by looking at the 1% worst case scenarios, the value at risk is the most optimistic measure of a bad case outcome, as it takes the highest return, smallest loss of all these cases. In other words, it tells you the investment loss at the first percentile of the return distribution, but it ignores the magnitudes of potential losses even further out in the tail. A more informative view of downside exposure would focus instead on the expected loss, given that we find ourselves in one of the worst case scenarios. This value unfortunately has two names, either expected shortfall ES or conditional tail expectation CTE. The latter emphasizes that this expectation is conditioned on being in the left tail of the distribution. ES is more commonly used terminology. Using a sample of historical returns, we would estimate the 1% expected shortfall by identifying the worst 1% of all observations by taking their average. Lower partial standard deviation and the Sortino ratio. The use of standard deviation as a measure of risk when the return distribution is non-normal presents two problems. One, the asymmetry of distribution suggests we should look at negative outcomes separately. And two, because an alternative to a risky portfolio is a risk-free investment, we should look at deviations of returns from risk-free rate rather than from the sample average, that is at negative excess returns. A risk measure that addresses these issues is the lower partial standard deviation, LPSD, of excess returns, which is computed like the usual standard deviation but using only bad returns. Wait, let me read this again because I sort of clocked out. Did not focus on the expected shortfall at all. So, it says here's the most optimistic from the viewer downside exposure, focus on the expected loss. As a worst case scenario, as to the expected shortfall ES, conditional tail expectation CTE. The latter emphasizes that this expectation is conditional on being the left tail distribution. ES is more commonly used terminology. The sample is talking about is the 1% expected shortfall, and for the worst 1% of all observations taking the average. Okay, that's fine. Lower partial standard deviation and Sortino ratio. The use standard deviation is measure of risk when the returns being non-normal presents two problems: the asymmetric distribution and negative outcomes separately. Because an alternative to a risky portfolio is a risk-free investment. Risk-free investment. We should look at the deviations or returns from the risk-free rate rather than from the sample average, that is at negative excess returns. Risk measure that addresses these issues is the lower partial standard deviation, LPSD, of excess returns, which is computed like the usual standard deviation but using only bad returns. Specifically, it uses only negative deviations from the risk-free rate rather than negative deviations from the sample average, squares those deviations to obtain an analog to variance, and then takes the square root to obtain a left tail standard deviation. The LPSD is therefore the square root of the average squared deviation, conditional on negative excess return. Notice that this measure ignores the frequency of negative excess returns, that is, portfolios with the same average squared negative excess returns will yield the same LP as D regardless of the relative frequency of negative excess returns. One sec, I again clocked out. I started thinking about other stuff. That's what happens, but I'm honest, it's okay. Let's do this again. Risk measure that addresses. Okay, one second. We should look at the deviations of the returns distributed rather than from the sample average. Negative. Yes, measure that addresses issues. Lower partial standard deviation (LPSD) of excess return is computed like the usual standard deviation, using only bad returns. Specifically, it uses only negative deviations from the risk-free rate rather than negative deviations from the sample average. Squares those deviations to obtain an analog to variance. Take the square root to obtain a left tail standard deviation. The LP SD is therefore the square root of average square deviations conditional on a negative excess return. Notice that this measure ignores the frequency of negative excess returns. That is, portfolios with the same average squared negative excess returns will yield the same LPSD regardless of the relative frequency of negative excess returns. Okay. Practitioners who replace standard deviation with this LPSD typically also replace the Sharpe ratio of average excess return to standard deviation, with the ratio of average excess return to LPSD. This variant of the Sharpe ratio is called the Sortino ratio. Okay. Relative frequency of large negative 3 sigma return. Um, okay, here we concentrate on the relative frequency of large negative returns compared with those frequencies in a normal distribution with the same mean and standard deviation. Extreme returns are often called jumps. As a stock price makes a sudden big movement, we compare the fraction of observations with returns 3 or more standard deviations below the mean to the relative frequency of negative 3 sigma returns in the corresponding normal distribution. This measure can be quite informative about downside risk, but in practice is most useful for large samples observed at a high frequency. Observe from figure 5.3 that the relative frequency of returns that are 3 standard deviations or more below the mean in a standard normal distribution is only 0.13%, that is 1.3 observations per thousand. Thus, in a small sample, it is hard to obtain a representative outcome, one that reflects true statistical expectations of extreme events. Let me read that again. This measure can be quite informative. One sec. Okay, we compare the fraction of observations with returns 3 or more standard deviation to the relative frequency of negative 3 sigma returns in corresponding normal distribution. Okay. They were quite informative about the downside risk, but in practice most useful for large samples of those at high frequency. Okay. Thus, in small sample, hard to obtain outcome one that reflects true. Okay, that was pretty nice. We just not discovered, but I mean, found out. I guess read about. We did read, yeah, that's true. We read about some tools and formulae that we use to estimate risk and expected shortfall, as we can see, and how much a portfolio can swing either way. But mostly we were focused on the negatives because that's what investors really care about mostly. Like, sure, everybody wants to make money, but what everybody wants more than anything is not to lose money, which is the most important part. Like, if anybody like did not make any, like if a portfolio manager came up with a break even, that is way better than coming up with like a loss. Obviously, I mean, it sounds pretty obvious, but it's like a mentality thing. Like, people would definitely every day like pick not making any money compared to losing money. That's why nobody cares about how volatile it is in the positive range. Maybe people do. Some people want those sort of risks and stuff, but most people truly care about how volatile it is that they're gonna lose money. Like, what are the odds that they're gonna lose money. That is a very important factor that goes into deciding if they want to invest with someone or in a fund, and so on. So therefore, we went over some some ways and some sort of estimators, you can say, of determining whether a portfolio um, is a good investment. Not completely vetting a portfolio, but some of the tools that go into the process, and it's pretty fun. The value at risk, the kurtosis, finally understood that. Like, I mean, I sort of understood it before as well, but this time it really hit home. With the like this book, it puts all the tools of stats and eco tricks into context, and really explains, like, it explains to you, like, for example, right now, when I was reading and looking at the graphs and stuff, I finally understood, like, if it's on the lower end, typically that means it's a loss, and the farther out it is, the greater the magnitude of the said loss, and the fatter the tail is, the more the probability mass, basically the more the odds are that you are going to have that great loss, and so on and so forth, like, kurtosis, skewness. So how standard if a distribution is skewed, the standard deviation doesn't really work in the sense of analyzing risk properly, since the data is skewed, and therefore we have to take different sort of approaches, um, to really, because not all distributions are going to be normally distributed, and some are going to be skewed. So therefore we have to take all these extra sort of steps and use all these different estimates to really grind down and see if the portfolio uh, is a good investment, or if it's not. And also we looked at the little tweaking done to the Sharpe ratio, and made into the Sortino ratio, where we have the lower partial standard deviation, which basically it's standard deviation takes both, right? It takes both the positive and the negative sides, but the point that they're trying to say is that if uh, yeah, if it's a non-normal distribution, that means when it's skewed, the the standard deviation doesn't really work. Therefore, we take the lower partial standard deviation, and that's essentially just taking the negative excess returns, because that's really what we're concerned with mostly, because investors don't really care, again, like I said, about the volatility and the positive returns. But so yeah, we take that, and then instead of using standard deviation like we do in the Sharpe ratio, where we divide average excess returns by standard deviation, we are now dividing average excess returns to lower partial standard deviation, and therefore we get the Sortino ratio. And other than that, we have all these other estimators, which are really nice and handy. And before that, we covered the normal distribution, finally understood that. So all this stuff is pretty cool, like, yeah, I just, yeah, I'm not even gonna say anything anymore. I'm just gonna keep doing stuff, and hopefully I keep doing stuff. I don't stop, essentially, is what I'm trying to say. Anyways, that's it. I have to go for cardio, actually. So yeah, anyways, thanks. It's day 40, so that's a nice thing, right? Next goal is day 50, and then day 100, and then so on and so forth. I hope this never ends. Anyways, yeah, thanks.